So we've done basic testing. Unfortunately, we had a few problems with the player just before we brought it into class to show you. So what we showed here wasn't really what we've been experiencing so far. It was working well. When it has full power, it works a lot better because there's a lot more energy going through the motor, so they can actually respond quickly and appropriately and how they should. So I guess the results so far were fairly good. We did encounter a lot of problems, and that's going to be presented a little bit later. So we'll just carry on to the next slide there. Coding and wiring. So when you look at the robot, you see the mechanical design. That's just one small system of the robot. It looks like the biggest, right? Because it's the first thing you notice. But behind every robot, there's a very complex coding and wiring system. So this is the wiring that we use on our board. And the reason that we have 4 boards is because each one of the boards is only capable of running 3 motors, and we have 11 motors. So we had to come up with a way to get the 4 boards to talk together. And standard practice is to have a master board and then 3 slave boards. So the master board sends a signal out to the slave boards. And I think there's a wiring diagram on the next page that shows it a little better. Hopefully this isn't too confusing. You have your master board up there. It's controlling some motors. You have your 3 slave boards. You have a transmitting pin with each of the slaves. So that's what sends the data saying, spin this motor, turn that motor, whatever. You also have a flow control pin. What this is the slave talking back to the master. So the slave says, or the master, sorry, says, I'm ready to send a signal. The slave then sends a message back saying, okay, I'm ready to receive a signal. So that way you don't have data getting lost in the transfer. From there, we just had a couple LEDs. I don't know if you saw them during the demo, just kind of flashing. Those were for coding debugging purposes. Then down here, the separate diagram. This is a wiring diagram for a kill pin. What this is it's the master outputs a constant 5-volt signal to each of the slaves through a wire. If that voltage goes down to 0 volts or the wire is disconnected, everything automatically shuts off. So it's kind of a fail-safe in case the robot starts to run rampage. It's conveniently colored blue, so just cut the blue wire and the robot shuts off. Or you can get the master to send a low signal over that line, and then the robot shuts off. So it's definitely a good safety precaution because when you have serial data, you're sending data continuously. And the slaves, if they don't receive that serial data, they don't know that they need to shut off. They don't know that they're not receiving the data they should. They just assume that the master is being lazy and not sending them any more data, so they just continue on. So that's why we had a flow control pin in there. So you just cut the voltage down there on 0 and everything shuts off instantly.
I'll discuss what we learned from designing and constructing the robot. The major issue was the conveyor belt. It was very important. It was very delicate as well. Initially, this one initially was wider. We had fabric glued onto every little piece of it, and that would help it carry more around. But we had problems with wear and tear of it. Small moving parts, and it's delicate, and it got damaged. So then we ended up just using this the thin conveyor that we had available. And on the moon, to design a conveyor belt, we needed to have a simple design with a lot of redundancy. So if a part were to break or damage, we can easily repair it, or it will still work even though some parts are damaged. And yeah, wear and tear is a big issue, especially on the moon. When the sun's facing the moon, it's very hot. When it isn't, it's very cold. Temperature switches, and the regolith is angular and has very sharp edges. So it has to be designed for that wear and tear. So material selection and design of wear and tear is very important. And we use a lot of batteries to power the conveyor belt, the bucket wheel, the chassis turning, and so on, the treads. And so on the moon, we would need a large power supply, and one that lasts really long on the moon, and solar power would be considered. And weight and motor issues. When we were testing the robot, we selected the motor size based on how heavy it was, and while we tested, we realized that heavier we had a stronger motor and a bigger size. And on the moon, once again, we would need to design for that, especially since there's less gravity. You got to take that into consideration. And bucket wheels. We actually had 2 bucket wheel designs. Here's the second one. The one we have right there, that one has a large, has a large slope opening at the top of the center, and where every single bucket has an opening that would fall in. And compared to this one, every single one had a sloped opening, so when it would spin, it would fall through here. But we found this one, the flour would get jammed in here, and it wouldn't be as efficient as that. So we ended up just using that one. And scaling up and implications. We found that simple design and modular design is very important on the moon. Just in case if anything gets broken or damaged, we can easily replace it. And we need a lot of redundancy. So even we can't just have one robot. We would think on the moon, if they were actually mining, we'd need many of these robots. If one was to break down or get damaged, it can be replaced or repaired while many others are still working. So you still have operation, continuous operation. And from what we've shown, like the technology is there for autonomous mining, but and helium-3 is also a huge energy source. But with further research into making autonomous mining more efficient to the point where it's economically feasible is needed, and also technology is improving rapidly, and also the price of technology is decreasing. So in the future, we think that it is possible to have helium-3 mining on the moon autonomously. And that will conclude.
I just want to say I want to thank everyone for listening to the presentation and got a good idea of what we worked on for this past year. And we'd be more than willing to take any questions at this point.
Well, the most important question that a mining engineer asks is, what's the production rate?
Depends on the bucket wheel speed is dialed up. On these ones, it's dialed up to the max of the servos, so we can get an idea for that, but we haven't got the exact dimensions yet for the final one, because as I'm sure most people know, it's not overly economically feasible to mine the moon. So we are kind of going more in generalities.
Okay, NASA held a competition a year and a half ago in which their target was 150 kilograms in 30 minutes. Did you meet that?
150 kilograms. I feel that if there was a way to do it, I think a bucket wheel would be the way to go, just because on their capacity.
Why did you decide on a bucket wheel?
Very good question. Yes.
Oh, the regolith is very soft and easily broken up right on Earth. We use bucket wheel excavators for a similar material that's like harder compacted than that. The regolith is very small. I mean, very soft and easily dug. And it also provides a continuous throughflow, right?
Yes, sir. I'd just also like to add, the quantities of helium-3 on the moon and the regolith are really low in the parts per billions. So you need something that can move a lot of material really fast, and we felt that based on Earth-based technology, a bucket wheel would be the way to achieve those throughputs.
Why else would you want to mine regolith?
Well, there's the potential for, I guess, ice and water for like rocket propellant, water storage people when we start colonizing the moon and other planets. It's really, really expensive to lift anything off of Earth, so it's beneficial if you can already have it up there. I mean, the moon isn't the best source because there still is a lot of gravity to get off, but if you go to an asteroid that's full of water, there's basically no energy required to lift it off of that asteroid, so it's a cheap way to get water, propellant, and stuff in space.
You mentioned gravity. I'm just kind of curious, and I really have no idea, but with the motion of the bucket wheel, when you're lifting it up and then you have low gravity, would you lose a lot more sort of just from it bouncing out and then you've got sort of suspended around your machine rather than getting collected? Did you have considerations for that, or?
Well, like prior to actually initializing production and manufacturing, we did the calculation between density that obviously we mentioned before that flour on Earth resembles that regolith found on the moon.
Okay.
In terms of conversion. And actually in the way that we designed the bucket wheel itself is that we considered a front motion to pick it up instead of pulling it out. And so to consider that material will go flying out and then we'd start losing it, right? So in that case, it would just be a matter of scooping it and then keeping some sort of embankment to keep it held down at the same time collecting it. So we have considered that and like the turbulence it would cause otherwise, right? So yeah. Yeah.
So what are the are you going to mine it day and night?
High temperatures is one of the big issues, right?
Yeah.
I mean, no atmosphere, high temperatures. Here we're looking more at mechanical feasibility and systems rather than, because we run into a lot of roadblocks with those kind of considerations with whether we have the technology currently. It's a good idea though, right, to mine at certain schedules, and with continuous mining you can certainly spend
I was just curious, so you think the day would be harder or the night would be harder? Like what's the temperature at night?
Well, that's the thing is that during the day it's considering wiring either flaring up, right, due to like increased temperature, or during night when it becomes extremely cold. So given the night and day cycle on the moon, we were considering to be in a state of hibernation during the day. It has to actually be able to, and in that case it would be some sort of sheltering system, has to actually harness the power, and obviously it would primarily run on solar power, given its abundance out there. So during the day it would be stored and protected, at the same time absorbing the power via some sort of transformer system, and then during the night it would start to operate. In that case it would actually be. I mean, again, our project was focused primarily on the technicalities, but to actually encompass a schedule and a layout, like you saw, Niko pointed out, our initial design is efficient, given its theatrical looks. But yeah. Okay. Yes.
So you have a pretty interesting pattern for which the robot follows. Just wondering how actually do you tend to get the material from the tail of the conveyor on the robot to the mill location following that pattern? It's pretty complex.
Yeah, excellent question. What it does, the regolith, or sorry, the helium-3 in the regolith is a solidified gas. So in the processing stage, which would occur on board in the central part of the robot, you heat the regolith up to 800 degrees, and that causes the gas to vaporize, and it can be collected, extracted, and just stored in a tank on the robot. And at that point, you have no further use of the regolith, so you just dump it off the back, right where it was taken from.
So you're just processing it on
And
board.
then you bring the gas tanks back to the central processing facility, where the helium-3 is separated from the other gases.
We mentioned it in the first couple presentation. We just didn't want to focus on it because we didn't want to mention it because we didn't want to focus on that. We were focusing more on the collection aspects. Right. And we've just simulated that it dumps it off the back.
Yeah.
So it will be, I think, 99% of the weight is coming off the back, right?
Right. Yeah. Again, like the emulation within the chassis in the main section is supposed to showcase that processing application. So then again, it will just get positive feedback. Yes, Betty.
Is there a lot of concern with tipping over?
That was definitely one of our big issues.
We couldn't find 1/6 gravity environments to test it. I don't know why.
Well played, Niko.
But yeah, definitely there's a lot of weight at the front of the robot with the bucket wheel. So we kind of tried to offset by putting the battery pack at the back. And the conveyor sticking out the back also has quite a bit of weight. So in the model here, it's fairly well balanced. It leans forwards a little bit, but it can do full 360 rotation with like a full load in the bucket wheel without tipping over.
Have you contacted any of the teams that are entering the Google Lunar Express? They're looking for a robot to go to the moon.
I haven't contacted them, but it's definitely, we've discussed talking about what we can do with the robot now, because it feels like just no ways to give the presentation report, you know, so we're kind of looking for like a competition we can enter it in or something.
Oh, you could actually get it.
Well, I was speaking about Pod earlier today, just talking about for robotics and how competitions are going. But again, our scale is actually much smaller.
Okay, one more question.
Yes.
Not a question. I mean, if you're looking for something to do, and any of you want a job with companies that are doing automation, I bet you if you sent them a video of this and the work you've done on it, they would be all over you. I
Well,
gotta admit.
that raises one other point. NASA is looking to hire mining engineers.
Yeah.
Yes, so.
Okay, well, thank you very much.